The comparison tests. There are two comparison tests. We start with the more basic of the two. This one's called the direct comparison test. Suppose that we have two series, summation of AN and summation of BN. And suppose they are both positive term series, meaning that all the terms of each series is positive. If the summation of Bn is convergent, and An is less than or equal to Bn for all n, then the summation of An is also convergent. So if you have a series An is less than a series Bn, and the series Bn converges, then the smaller series also converges. Likewise, if the summation of Bn is divergent, and if An is greater than or equal to Bn for all n, then the series summation of An is also divergent. So if a series diverges, then a series that is larger than that also diverges. For example, determine whether the series summation n equals 1 to infinity of 5 divided by 2n squared plus 4n plus 3 converges or diverges. Well, first, let's think about the general behavior of this series. So we have the sum n equals 1 to infinity of 5 divided by 2n squared plus 4n plus 3. Now, as n gets very large, these terms don't matter too much because 2n squared is going to be so much larger than 4n or the number 3 that these are pretty much negligible in terms of the behavior of the series. So what I can say is that this series roughly behaves like the sum n equals 1 to infinity of 5 divided by 2n squared. And again, this is because as n gets very large, these terms don't matter very much compared to the squared term. But we also know that 5 divided by 2n squared plus 4n plus 3 is definitely less than 5 divided by 2n squared. Notice that these two fractions have the same numerator, and they both have the term 2n squared in the denominator, but this one has two extra terms added to the denominator. And so we know that 2n squared plus 4n plus 3 is larger than 2n squared. So if we take the number 5 and we divide it by a larger number, that is going to be smaller than taking the number 5 and dividing it by a smaller number. So we know that this is true for all values of n. Then the big question is, what does this series do? Does this series here converge or does it diverge? Well, this series is equal to 5 halves times the summation n equals 1 to infinity of 1 over n squared. And we know what this series does because this is a p series. And it's a p series with p equals 2, and 2 is bigger than 1. Therefore, this series converges. Now, when I say this series, I am talking about this series right here. But we also know that if you have a converging series, multiplying it by a constant does not change whether it converges or diverges. So if this series converges, 5 halves times that series also converges, and that means that this series converges. So here we have a converging series, and now we know that the nth term of this series is less than the nth term of this series. Therefore, by the direct comparison test, we know this series must also converge. So we'll go ahead and say, therefore, by the direct comparison test, the summation n equals 1 to infinity of the series in question here also converges. In the next example, we have the summation of the natural log of k divided by k from k equals 1 to infinity. What does this series do? Well, first, let's just state a fact that the natural log of k is going to be bigger than 1 if k is greater than or equal to 3. So if you plug in a number that is larger than or equal to 3 here, the natural log of that number will always be bigger than 1. And since that is true, then we know that the natural log of k divided by k will be larger than 1 divided by k, again, if k is greater than or equal to 3. But that means that this series, k equals 3 to infinity of the natural log of k, is going to be bigger than the series k equals 3 to infinity of 1 over k. Right? Because this is larger than this for all values of k greater than or equal to 3. But we know that this series diverges. And we know it diverges because it is the harmonic series. So we can actually call this series out by name. It's a special series. It's the p series with p equals 1. And remember, if your value of p is less than or equal to 1, we know that it diverges. But this one in particular is called the harmonic series, and we know it diverges. And so if this series is greater than this one, but this one diverges, meaning that this one adds up to infinity, then that proves that this one also diverges. Now you might ask the question, well, how do we prove that this diverges then, because you have k equals 3 here? Well, let me ask you, if we have the series k equals 1 to infinity, and we know that it diverges when you add it from 3 to infinity, is adding 2 additional terms to this series going to make any difference as to whether it converges or diverges? And the answer is no. Any finite number of terms, if you add them to a series or take them away from a series, does not affect whether or not the series converges or diverges. So what I'm saying is, if we know that this series diverges, then we know that the sum k equals 1 to infinity of the natural log of k divided by k must also diverge. And again, this is from the direct comparison test. The direct comparison test is a great test to use if you can easily show that one series is greater than another series, or if you can show one series is less than another series. But sometimes it's difficult to actually show that one series is less than or greater than another. So we have another comparison test called the limit comparison test. And it says, suppose we have two series that are both positive terms. If the limit of the nth term of one series divided by the nth term of another series is equal to some number c, where c is a finite number, meaning it cannot be infinity, and also c is positive, then either both of the series converge or both of the series diverge. So the way this works is, suppose you are trying to figure out whether the summation of an converges or diverges. You're going to choose a series to compare it to, and the series that you're comparing to has to be a known series, meaning you already know whether this series converges or diverges. And then when you take the limit of the nth term here divided by the nth term here, as long as that limit produces a positive constant, c, then both series must behave the same way. So consider this example. Test the series summation n equals 1 to infinity of 1 divided by 2 to the n minus 1 for convergence or divergence. Well, this is not a known series. We don't know if this converges or diverges. But there is a series that is very similar to it for which we do know if it converges or diverges. And so this series that we're looking at here behaves very much like the series summation 1 to infinity of 1 divided by 2 to the n. And understand, all I'm doing here is ignoring the negative 1 because this negative 1 is insignificant as n gets larger. What does this series do? Well, this series converges. And we know that it converges because this is a geometric series. With r is equal to 1/2, and the absolute value of 1/2 is less than 1. Therefore, we know it's a converging geometric series. So now to apply the limit comparison test, I'm just going to take the limit as n goes to infinity of the nth term here, which is 1 divided by 2 to the n minus 1, over the nth term here, which is 1 divided by 2 to the n. If we do a little bit of math here, just to write this without having a complex fraction, we can say this is 2 to the n over 2 to the n minus 1. Clearly, this limit is infinity over infinity as n gets large. And so therefore, we can get this limit by using L'Hopital's rule and taking the limit as n goes to infinity of the derivative of the numerator. So let's remember the derivative of 2 to the n is 2 to the n times the natural log of 2. And we're going to divide that by the derivative of the denominator. Well, the derivative of 2 to the n, again, is 2 to the n times the natural log of 2. And then, of course, the derivative of negative 1 is 0. And so this limit ends up being 1, right? Because all these cancel out. Well, 1 is a constant c, right? This is our constant c. C is not 0. C is less than infinity. So as long as we get a value of c that is somewhere in between 0 and infinity, this means both series behave the same. Well, again, we already know that this series converges because it is a geometric series. So therefore, both series converge, right? By the limit comparison test, both series have to have the same behavior in terms of convergence or divergence. And so the limit comparison test is a pretty simple test to use. I mean, the hardest part about it is sometimes just taking this limit. You'll have to remember rules for taking limits, such as L'Hopital's rule, etc. And the other thing is you'll have to choose to compare it to something that you know how it behaves. So what you're going to choose to compare it to needs to look something like the original. It's going to be kind of a simplified version of the original. And then you have to make sure that you know the behavior of that. Otherwise, if you don't know what this series does, then you won't know how to conclude the problem in the end. One final example here, we have the sum of 2n squared plus 3n divided by the square root of 5 plus n to the 5th power. Okay, so we want to know, does this converge or diverge? So let me go ahead and write down the original series here. And we're going to say that this behaves like what? Well, we're going to eliminate anything that is not significant here. So in the numerator, as n gets really large, 2n squared is much bigger than 3n. So when you plug in, think about numbers that are, trillions or whatever. When you plug in extremely large numbers here, the quantity you get here is going to make this quantity insignificant. So the numerator is going to behave like 2n squared, or you can even say that it just behaves like n squared, because even the 2 is not really that significant. And then the denominator, you have the square root of 5 plus n to the 5th. The 5 really doesn't contribute much, right? I mean, as n gets really large, this number is going to be so big that it's not really going to matter if you're adding 5 to it or not. So the denominator behaves very much like the square root of n to the fifth. Now the square root is significant, but the 5 in front of the n to the fifth that you're adding is not significant. Now we just got to say, well, how does this series behave here? Well, let's simplify it. What we have here is n squared, and then the square root of n to the fifth is n to the 5 halves. And then we can rewrite that by subtracting 2 minus 5 halves. You don't necessarily have to show this step, but this is going to give us n to the negative 1/2, which is 1 over the square root of n. And this is a p series with p equals 1/2, and 1/2 is less than or equal to 1. Therefore, we know that this series diverges. Okay, so we are comparing our series to this series, which is a diverging series. So we expect that this series is going to diverge, but you have to do the limit, because if you made some kind of a mistake in terms of what you chose to compare it to, that will bear out in the limit. So we need to take the limit next. So we're going to do the limit as n goes to infinity. We'll take the nth term of the series in question. And we're going to divide that by the series that we are comparing it to. Now, when I do the comparison, so when I put the one that we're comparing to down here, I could choose the simplified version, but actually instead I'm going to choose the version before we simplify it. Because what's going to happen here when you do that is you're going to get a little nicer cancellation when you bring these together. So this is going to be the limit as n goes to infinity, 2n squared plus 3n over the square root of 5 plus n to the fifth. We're going to multiply by the reciprocal, square root of n to the fifth over n squared. And then we're going to rewrite this by grouping these two terms together. So I'm going to put 2n squared plus 3n over n squared. And then times we have the square root of n to the fifth and the square root of 5 plus n to the fifth. Now I'm being very detailed here, showing all my steps. So we have 2n squared plus 3n still, divided by n squared. Now what I'm going to do here is combine these into a single radical. And now we'll use properties of limits, which basically say that we can take the limit of the first one and multiply it by the limit of the second one. So we have the limit as n goes to infinity, 2n squared plus 3n over n squared. And we're going to multiply that by the limit as n goes to infinity of the square root of n to the fifth divided by 5 plus n to the fifth. One more property of square roots, we can take this limit and we can move it inside of the radical. That is it's actually a property of limits that you learned quite a long time ago. So we have multiplied by the square root of the limit of n to the fifth divided by 5 plus n to the fifth. Okay, now we just need to evaluate these limits. This limit here is infinity divided by infinity, so you could use L'Hopital's rule. Same thing here. This limit inside the radical is infinity divided by infinity, so you could use L'Hopital's rule as well here, which would involve taking derivatives. Or you could use the fact that when you have a rational function like we have here, if the degree of the numerator and denominator are the same, the limit is going to be the leading coefficient divided by the leading coefficient. Same thing over here. Degree of numerator and denominator are the same. The leading coefficient here is 1. The leading coefficient here is 1. So this limit is going to be 2 divided by 1, and this limit is going to be 1 divided by 1. Now, I think I will go ahead and proceed using L'Hopital's rule. And if we use L'Hopital's rule, we get the limit of the derivative of the numerator, which is 4n plus 3, divided by the derivative of the denominator, which is 2n. Then we're going to multiply that by the square root of the limit of the derivative of the numerator here, which is 5n to the fourth, divided by the derivative of the denominator, which is also 5n to the fourth. Now this limit, interestingly enough, is still infinity over infinity. So I'll use L'Hopital's rule again. And so this limit becomes the limit of the derivative of 4n, which is 4, divided by the derivative of 2n, which is 2, multiplied by the square root, and we already said this limit over here is equal to 1 because these cancel out. And now we have the limit of 4 divided by 2, which is 2, times the square root of 1, which is 2. And so we get a value, c equals 2, c referring to the limit comparison test. And that value of c is a number between 0 and infinity. Therefore, we know that both series behave the same. So now we have to go back to the beginning. How did this series behave? Well, we already said that it diverges because it was a p equals 1/2 p series. So now we know that both series are going to diverge. So the series that we're testing diverges according to the limit comparison test. And that concludes this video lesson.